In this video lecture, we will have a first look at the theory behind the lasso. We're not going to go very deep in the theory. It would be extremely interesting, but also would take all of the course to just cover the theory behind the lasso. So what we will do instead is we will focus on important results, important assumptions, and in particular we will focus on how to interpret them. So we'll not focus on the theory for the theory as such, but instead we'll focus on the theory and what do we learn from the theory that can help us when we actually apply these methods in practice. Now the first thing to note is that I will be using several asymptotic results here that I expect you to be somewhat familiar with, at least. There is a separate file on Canvas which gives an overview of the most important asymptotic results that are needed for this course. In particular, what we need are things like central limit theorem, law of large numbers. And in that presentation, I also show how to apply them to the standard regression setup, where we derive the asymptotic properties of least squares estimation. So have a look at those slides and use those to refresh your knowledge about that. In general, I will come back to things when it's needed to introduce new material or its specific points of interest. Now, we will do asymptotic analysis, but we should realize that asymptotic analysis is in high dimensions different than usual. So what do we normally do? We take our sample size n and we let n go to infinity. We say what happens when n goes to infinity? Well, we know that if we look at the sample mean of n observations, we say n goes to infinity, then we can apply the central limit theorem to show that the sample mean, if we scale it correctly, converges to a normal distribution. What we also do, if we look at, say, the regression framework, we look at least squares estimation, we take the number of regressors p to be fixed. It's important to realize that this framework does not cover high-dimensional models. In high-dimensional models, what we actually have, we've looked at when we looked at the curse of dimensionality, the problem was p is large relative to n, and then everything goes wrong. But if you do this asymptotic framework, where you say n is going to infinity when p is fixed, then you will always reach the point where n will be much larger than p. So you might start off with p being equal to 1 million, but infinity is much larger than 1 million. So if you would do this framework, then you would basically find always that, for instance, least squares works fine. No matter how large p is, as long as it's fixed and not growing with n, least squares will do fine. So we will not need any regularization. We do not need to use the lasso or anything that we do in this course. So we don't want this kind of assumption. We don't want to work under this framework because it will not give us meaningful, insightful information. So what we will do instead is we'll let n go to infinity, but also p to infinity. So that means if you have more observations, you also have more variables. And this is to counterbalance that. We let n go to infinity. But because we don't want the number of observations to dominate, we want to make life hard for our method. So if n grows, p must grow too. So in general, we only write n going to infinity, but what we mean is that p is a function of n and grows along with n. And it can grow at different speeds. And I will come back to the speeds at which it can grow. Now, we will start and we'll occasionally do look at this framework, the standard framework, simply as a first step, and also because life just gets very complicated in this framework. But keep this in mind when we do asymptotics. Now, the most basic thing we can look at is consistency of an estimator. So we want our estimator beta hat to be consistent for the parameter beta. Well, when is that the case? Well, whenever the distance between beta hat and beta becomes smaller than epsilon with high probability. So if you let your n to go to infinity, beta hat will go closer and closer to beta, such that the probability that this is smaller than epsilon will always be 1 in the limit for any epsilon, no matter how small we take it. Or the probability that the distance is larger than epsilon is going to 0. So we typically write this as with this arrow indicating convergence in probability. We also use the stochastic order notation given here. So if you took the time series course, this will be very familiar to you. If you did not, again, have a look at the slides that are posted on Canvas where this notation is explained. So what it says roughly is that beta hat is equal to beta plus something, which is going to go to 0. So this small OP1 indicates that it will go to 0. Now, we will need to extend that to vectors because we don't have one parameter and one estimator, we have a whole vector of them. Well, again, here we have an issue where in standard asymptotics, this is no problem whatsoever because we can just look at each element separately. And if each element converges to its respective parameter, then the whole vector will also converge. And no matter how we measure it, it does. So for instance, we can take the L2 norm of the vector. We could also take the L1 norm or the L infinity norm. They're all equivalent. If every element in that vector converges in probability to the limit, then the whole vector will also converge to the limit. So this is the case for fixed dimensional vectors, right, where the dimension p of the vector is not increasing. Well, this is different if we have high dimensional setting. The argument why it doesn't matter in fixed dimensions is something along these lines. So compare the L2 and the L1 norm. If we compare those norms, you can work out, or just look it up on Wikipedia, that the L1 norm of a vector is always larger than the L2 norm. But the L1 norm is smaller again than square root p times the L2 norm, where p is the dimension of this vector. So of course, if p is fixed, that basically means, well, if my L1 norm goes to 0, then my L2 norm also goes to 0, and if my L2 norm goes to 0, my L1 norm also goes to 0. But for us, in the high dimensional framework, p will increase to infinity. So having my L2 norm go to 0 does not mean my L1 norm also goes to 0, because we would need square root p times the L2 norm to go to 0 for the L1 norm to actually also go to 0. So that's already one of the complications that we face, that actually it matters which norm we take. So convergence, consistency in the L1 norm is stronger than consistency in the L2 norm. Now, let's leave that aside for a moment and let's go back to the case where p is fixed. So I'm going to assume the classical framework and already show that life is already very complicated here in the classical framework. So there's a famous paper by Knight and Fu, who were the first to really look at the asymptotics of the lasso. Well, let's start with some good news. The lasso actually gives you consistency, as long as your penalty is going to go to 0 when the sample size increases. Well, we're not going to go through their arguments, but we can look at some intuition from taking orthogonal design. Remember, orthogonal design gives us an explicit expression for the lasso estimator of the jth element, being the soft thresholding estimator. So it's the sine of the least squares estimator times the maximum of the absolute value of the least squares minus lambda over 2 and 0. And so the thresholding is occurring if this part here is not larger than 0, then we'll set this whole thing equal to 0. So if beta at OLSJ is not large enough, not far enough away from 0, my estimator for the lasso will be set equal to 0. Well, now one thing we know in this case where n goes to infinity and p is fixed is that OLS actually is consistent. So the OLS estimator converges to the true value of the parameter beta. Again, we can write that here, the consistency result here without looking at norms, because we're in the fixed p case. So what we also know is that basically this carries over to continuous functions, and this function here, self-thresholding, is a continuous function of the least squares estimator. So we also know that for large n, this thing here will converge to this thing here, where you plug in the limit for the least squares estimator. So I'm going to write approximate signs here, where approximate really means it's an approximation for large n. So if n gets large, this will become approximately equal to this here, where we have the true values of the betas. Now, what we also know is we can write any number x as its sign times its absolute value. It might look complicated at first, but think about it. Take the number 3. Well, the sign of 3 is just 1. It's positive. The absolute value of 3 is also 3. Take minus 2. The sign of that is minus 1. The absolute value of minus 2 is 2. So you get minus 1 times 2 is minus 2. So this is, by construction, always true. And now note that what we have here is we have the sign of beta j, and we have the maximum of beta j absolute value, minus something else and 0. But the absolute value here times the sign is what we are after, because if we can get that, we know that's equal to beta j, and that would, we want our lasso estimator to converge to beta j. Now, there's this problem here with this lambda. So if this lambda is persistently being different from 0, you will always subtract something from your true beta j. And you may not end up with 0, you may be larger than 0, but you will not end up at the true value. Now, would lambda be equal to 0, of course, and we know beta j then is what we'll end up with here. Either it's 0 and we have 0, or it's larger than 0 and we have absolute value of beta j. And we can, of course, directly into this framework sign beta j times absolute value of beta j. So we need this lambda to disappear. So for large n, the lambda should disappear, should go towards 0. The penalty should not be too large. That is the practical implementation. You have, of course, you need a penalty, but it should not be too large. If it's too large, it's too much brute force, you will kill variables that you should not kill, you will have a bias that does not disappear. And this is, of course, exactly what Knight and Fu find. Now we want to look at what distribution this thing has, at least in the limit. So we're looking at convergence and distribution. I'll square root n times the beta hat from the lasso minus beta. And here life already becomes complicated, because we don't have a nice normal distribution for this thing. So what they show, in fact, is that the distribution, say let's call this limit distribution f that it has when n goes to infinity, it's such that the probability of the random variable having exactly value 0 is going to be larger than 0. And this is, of course, very problematic, because we know that, for instance, the normal distribution being a continuous distribution, well, the probability of ending up at any particular point is 0 by continuity. So here we actually have a limit distribution which is not continuous. There is point mass at 0. So this already makes life very hard, right? Because how are we going to construct, for instance, confidence intervals if we can't use the normal distribution to base our inference on, or do hypothesis tests? This is going to be one of the major issues that we need to solve later on in the course. But already here in this simple case where P is fixed, we have problems. Now let's again see if we can get some intuition from the orthogonal design case. So take the orthogonal design case. So this Q here is a typo, so it just be, as usual, x prime x over n being equal to the identity matrix. Now, take also for simplicity sigma squared equal to 1 in the regression model. And what we are going to do now is going to use that, in that case, the least squares estimator. Again, have a look at the slides that are on Canvas, where I derived the limit distribution of the least squares estimator. Of course, you already did that in earlier econometric courses. But if you're not familiar with it, or it's too far away, have a look at those slides. But what we can see there is that in this particular case of orthogonality, the least squares estimator will have an asymptotic distribution, mean 0, and a variance equal to the identity matrix. So in general cases, we would have something like sigma squared times x prime x inverse there. That is gone because of the orthogonality assumption and the fact we assume the variance of the error terms is equal to 1. So we start from this point here, the least squares estimator, which has an asymptotic distribution of standard normal, multivariate standard normal. Well, I'm going to write that slightly differently, simply because it allows me to be a bit more flexible with writing. So I'm going to say this quantity here, square root n times beta hat OLS minus beta, is approximately equal in distribution, which is what the D indicates, to Z. And Z is just a standard normal. So I'm not saying the same thing as I'm saying here, I'm just writing it differently. So I'm just saying, take square root n times beta hat OLS minus beta, and we can treat it as if it's a standard normal, at least when n is large enough. That's what the approximate sign says. Now the nice thing about using this notation here is that I can manipulate this statement. So I cannot do that with these arrows, because then I need to have limits on the right hand side, and that I don't want. So what I want instead is to say, well, what about beta hat OLS itself? Well, I can just divide by square root n on both sides here. So I get a term z divided by square root n, and then I add beta. So if n is large, beta hat OLS will be close to beta plus something which is standard normal divided by square root n. And this, of course, we can do for each element. Right, so rather than looking at the whole vector, we look at specific elements. So the jth element of the least squares estimator is approximately distributed as beta j plus something standard normal over square root n. So we can of course also combine this in one go and say it's approximately normally distributed with mean beta j and variance 1 over n. Now I'm going to use the same heuristic argument as I did before to the lasso. So I have the exact expression for the lasso. It's the soft thresholding estimator, and I'm going to now again replace the beta hat OLS here and there with its distributional limit. Again, I can do this because it's a continuous function, and the continuous mapping theorem tells me that this is allowed. So I'm going to just replace that. It's not going to be very helpful at this point, right? We just have a weird expression here. But now we can do some calculations with this. And what I want to calculate now is the probability that my estimator is going to be equal to 0. That will tell me something about this thing which I said was happening in the limit distribution. So if my estimator is to be set equal to 0, that means that this maximum here should occur not on this point, but it should occur at 0. So it will happen if this first part here is smaller or equal to 0, then my maximum will be at 0. Well, when is this part here smaller than 0? Well, whenever the absolute value of beta j plus zj over square root n is smaller or equal than lambda over 2. It follows directly from the condition here. Well, I can write this out. I can write out the absolute value. So I get a lower bound and an upper bound. And I can just, and then at the end, make sure I only get zj in the middle. So I'm going to get the beta j to the outside. And I get this expression here, this probability here. Well, given that this is just standard normal as zj, I can calculate this easily. I just have I need to plug in values and then I can calculate it from the normal distribution. Now, we don't actually have to go calculate it, but let's just take the case where beta j is equal to 0. That's the easy case, because then these betas will cancel out, will drop out here. And then this probability that my estimator is going to be equal to 0 is, for large n, going to be approximately equal to this probability here. So that zj is in between square root n lambda over 2 and minus square root n lambda over 2. Well, if this bound, if square root n times lambda is not going to 0, then you will have something negative and something positive, and that being in between. Well, then we know, of course, that for the normal distribution, the probability of that is going to be larger than 0. The only way we can get this 0 would be if square root n times lambda is actually converging towards 0. Because then you get zj in between 0 and 0. But if that's the case, you have an extremely weak penalty. Because even if you blow it up with square root n, it still converges to 0, and you're basically doing these squares. So this indeed shows that, yes, in this case, we actually find that the probability that even in the limit our variable, our loss estimator is going to be 0 is larger than 0. And since that persists, it means that it will end up in the limit distribution. So now what we want is to let p grow with n. So we want to really go to the high dimensional setup, and we want to let p grow to n. Now at this point, asymptotics and also the approximations and the heuristic arguments that I used in the previous slides will not work anymore. Instead, we have to use different arguments. So standard asymptotic analysis becomes very complicated because you have these two dimensions which are growing. So typically what people do is they derive small sample bounds. So they basically derive bounds, for instance, on beta hat minus beta, that hold actually in finite samples. And then we can extend that to asymptotic results. So if you're interested in that, we're not going into that in this course. If you're interested in that, I recommend these chapters from the books that you can find on Canvas. Let me go to the parts that matter for us. What do we need to know if we want to apply things? And the first thing we need here is sparsity. So far we have not used sparsity yet. So let, as before, curly S0 denotes the true set of relevant variables. So S set is those j's for which beta j is not equal to 0. Again, we can also use the approximation if we don't believe that a true model is sparse. S0 is a set which is known to the oracle, which is the best sparse approximation of the truth. And then we have the definition of and the condition on sparsity. Say small s0, which is the number of elements in that set. So the number of relevant variables should be small. What does small mean? In this case, well, it's this particular rate, which is not very meaningful in itself. So I also don't want to dwell too much on that. Basically, it may increase, but it should never increase more than square root, or even as the same rate as square root n. It should increase. Small o means at a slower rate than what is in here. So slower than this rate that we find in there. In practice, what does it mean? We can have some relevant variables, of course, but not too many. So, well, suppose you're in a situation where you have 100 variables and you believe that 80 of them are relevant. that is not sparsity. That is not going to be, you're not going to get what you want there using the lasso. On the other hand, if you believe that 10 are relevant, then you're much more in a setting which is appropriate here. Now there's an alternative way to define sparsity, which I think is quite interesting as well, because it also comes back to the issue of approximations and whether we believe that the models are true models are really sparse. And that is so-called weak sparsity, where we don't look at the L0 norm, which we do for regular or strong sparsity, but instead we look at the L1 norm. And what we're saying is the L1 norm, so the sum of the absolute values, should not be too large. Now, of course, if actually many of the beta j's are 0, so we are in the standard sparsity case, then of course that already means that many of these elements in the sum drop out and the sum will not be too large. But this also allows for a different setting. So this is more general than the regular sparsity because it also allows for a large number of small coefficients. The idea then is that these coefficients, even though they are non-zero, they are so small that they actually do not matter that much. So if we set them equal to 0, if we do not choose those variables in our model, we don't actually lose much. There are not really consequences of that. And I think often in practice, this is a much more defendable setting of weak sparsity rather than strong sparsity. Again, the rate that we have here is the same. So if you, for instance, think about time series models, and we think about autoregressive processes, then this actually translates to a summability condition, where we say that the sum of these coefficients, if we move further into the past, should not grow too large, which is a very natural condition in a time series model. So actually, summability can be linked to sparsity. So if you have decaying autocorrelations, that you can link that actually. It's one particular form of weak sparsity. Let's look now at our first result, which is called prediction consistency. So it's a form of consistency, but it's a bit different than the regular parameter consistency that we usually consider. So parameter consistency says something about, because beta hat for beta, here we don't do it directly on the betas, but we do it on the predictions. So predictions are x prime beta hat, if we want to predict y. And we're going to compare that prediction to the mean of a prediction, because this is the best principle we can do. We're not going to compare it directly to y, because we know there's always an error term. Well, we only want to have like the mean parts that we can predict, so x prime beta. Now, this is weaker than the betas themselves, because of course it's sufficient. If beta hat converges to beta, then of course x prime beta hat minus beta will also converge to 0. But this allows for a bit weaker, because we may mess up our betas as long as it does not affect our prediction through x. This is of course related to what I was mentioning before. If you do prediction, you don't particularly mind if you get some of the elements wrong, as long as they don't matter too much. Right? If some coefficients are 0, but you estimate them as non-zero, as long as they're not too big, they will not affect your prediction. So this is the weakest form of consistency we can consider. And what we have here is that if we assume sparsity, either weak or strong, we can get indeed this form of consistency. So in particular, the weakest result we get without any additional conditions is we need to let lambda grow at this certain rate. So lambda will have to go to 0, but it must grow to 0 at this particular rate, so it should also not go too fast. And if that happens, then we indeed can show without any additional conditions that we get in terms of the expected value of the prediction error, we get consistency. Now if we make the results a bit stronger, and if we add something called a compatibility or a restricted eigenvalue condition, then we can show what is called an oracle inequality. I will come back to these conditions in a bit. Let me first focus on this result here. It's again a prediction consistency result, but it gives us a specific rate. So here we just say it goes to 0, so it's small p1. Here we actually know the rate at which it goes to 0. And the interesting part about that is that we can compare it to how well the oracle that knows the true set of relevant variables, how well that does. And what we can show is that the oracle has a rate of S0 over n. We have times LMP for the lasso. So what we are doing worse than the oracle is this factor LMP here. So the loss of not knowing S0 but using the lasso instead is LMP. And this is actually a remarkable result if you think about it. So the oracle, which has all the knowledge about the relevant variables, only does a tiny bit better than we do, because the logarithm of p is going to be something very small. So that means that we hardly lose anything towards the oracle. Right? And that's where the name oracle inequality comes. It tells us how much worse do we do than the oracle. So let's go back then to parameter consistency, which is a stronger result and is the usual form of consistency. Now, as I already mentioned before, it matters which norm we take. So L2 norm is not the same as L1 norm. So if you have L2 norm consistency, you don't have L1 norm consistency by default. The other way, of course, you do, because this is a bigger number than that one. So if this goes to 0, and that must also go to 0. Now again, we can show that we actually have this parameter consistency. So we again need this growth rate on lambda. And we need, again, a so-called restricted eigenvalue or compatibility condition. Again, we can compare to what the oracle does. And the oracle, again, is square root of log p better here. So again, we hardly do any worse than the oracle, which is remarkable. So even though you may have 1,000 variables and 10 of them are relevant, we don't know which ones are relevant, but the oracle does, but we still hardly do any worse than the oracle if we look at consistency, which is a very powerful result for the lasso. Now, to round up, I will discuss what do we take away from these results and what do we take away from these conditions. But before that, let me briefly go into the restricted eigenvalue and compatibility conditions. This is going to be a bit abstract, so please bear with me or take a cup of coffee for the next 2 slides. So what we need is a set of relevant variables. That is the first thing we need. Then for that set of random variables, we can define a restricted eigenvalue or compatibility condition. I'm not going to go into the difference between the two. There are many variants. I will describe something which is sort of an intersection of all of these. So take all vectors beta for which the L1 norm of the complement of S0, so the L1 norm of all the irrelevant variables, is going to be smaller than some constant c, where c should be larger than 1, of the L1 norm of the relevant variables. And now you might wonder, well, isn't this thing not always 0? If the irrelevant variables don't have coefficient 0. Of course, yes, in population, they do under strong sparsity. But this should hold not just in population, we're actually also will be needing this for our estimators. And in particular, our estimators minus our true values. That's what we're going to be needing this for. But we need that the L1 norm of the complement of S0 is small compared to the L1 norm of S0 itself. And for those betas which satisfy that restriction, what we then want to have is the following condition. So take the L2 norm of beta and squared, multiply it by some number phi larger than 0, then we want this quantity to be smaller than the L2 norm of x times beta over n. We can write this, of course, out. So this is beta prime x over n times beta. And we want this to hold with high probability because, of course, x may be random, and then we cannot say this holds for certainty. So, but it should hold with very high probability, in fact, probability going to 1. Now, this is, of course, very abstract, and this condition is not very easy to understand whatsoever. Now, let's see if we can link it to eigenvalues. I mean, as you can imagine, given the fact that this condition is called restricted eigenvalue, it should be linked to eigenvalues. So, and in fact, we can. So we can show that if you take a symmetric matrix A and you look at the smallest eigenvalue of that symmetric matrix, then the smallest eigenvalue times x prime x is going to be smaller or equal than x prime A times x for any vector x. So this looks very much like what we have in this condition here, where we have our x is now beta and our A is capital X prime capital X over n. So if we could look at the smallest eigenvalue of this quantity here, x prime x over n, and if that would be positive with high probability, well, then we could just take our phi equal to that smallest eigenvalue. And we would be done, and this condition would be satisfied. Now, in eigenvalues, then that is something we actually can say something meaningful about. But once we do try to say something meaningful about that, we also realize directly that if n is smaller than b, so there are more regressors, more variables than observations, then what we've already seen is that this is not an invertible matrix and the smallest eigenvalue is 0. Right? We cannot calculate the inverse. And of course that is a problem because then we cannot use mu min because we really need this phi to be larger than 0. So what we are going to do is, instead of saying it should hold for all vectors, because if we would use the eigenvalue, it would hold for all vectors beta, but let's restrict that to the set where the betas in the subset S0 are much larger than, or are larger than the betas in the complement of that set. So what we're almost doing is we're setting this thing close to 0. Suppose it would actually be 0, then you would only look at eigenvalues of a subset of variables. So you would look at only the columns in S0 of x prime x. This will of course become a much smaller matrix, because if you only look at this matrix here, the number of variables that are in there are the number of variables in S0. And those will be smaller than n, because that is exactly what sparsity tells us. Sparsity says there should be, the relevant variables should just be few. So in that case, if you have few relevant variables and you look at the x prime x matrix of those few relevant variables, that is much more likely to have a minimum eigenvalue larger than 0, because, well, already the dimension is smaller than n. So we need a small set of S0, which is what the sparsity condition gives us. And if that is indeed the case, then the eigenvalues are much more likely to actually satisfy that relation. And in fact, you can show that indeed for many data generating processes, these conditions actually hold. Now, there's somewhat of an issue sometimes, because people tend to, in theoretical work, tend to just assume that a condition like this is true without actually investigating it. And there are cases, and for instance something that we looked at with unit root variables, Again, for people with a time series will be very familiar doing regression with unit root variables. Take co-integration, right? Then there, if you would want to apply the lasso, actually it's very problematic to show that these conditions hold. So we should be a bit careful with these restricted eigenvalue conditions, but at least, I mean, for us in general, I would say the practical takeaway is if you don't have time series variables which have unit roots, you're pretty much okay using the lasso. If you do, you should be a bit careful. So let's summarize and let's get away from all the theoretical results and try to bring it down to something that we can actually use for us in practice. So first thing we need is to think about the rates that we had. And in particular what we need for consistency, because this rate popped up in all of the rates of our errors made by our estimator, is that S0, the number of relevant variables, times log p divided by n should go to 0. So what does that mean? Well, first, what does it mean for p? Well, p cannot grow as fast as e to the power n. And that's not really saying much, obviously, because e to the power n is really, really fast. So what we can have, and that makes it even more remarkable that we are almost doing so well as the oracle, is we can really have thousands of variables, even if we only have 50 or 100 observations. Which, well, I mean, you would be sort of a hopeless situation, you would think. But actually, it's something that the lasso can handle. It can deal with it. So, for instance, in genetic applications, people do this. They only have a few observations, but they have thousands and thousands of genes. I would say in economics, we don't have that many variables. We can be lucky if we have the number of variables approximately equal to our sample size. Well, clearly that satisfies this restriction. So here we're safe in economics. Now there is a catch, and I'm not really mentioning that yet, but this all does rely on having relatively small error terms in your regression models. Particularly, we should not have fat tails or outliers. If we would, then we would not have these wonderful rates anymore. And that is, of course, going to be a problem in economics. But that I will discuss in more detail later when I discuss applications to economic problems. Now, the other thing that we need is, of course, S0, the number of relevant variables. We've already discussed that a bit. It should be small. It may grow, but it should grow small. Should grow very slowly. And it also is affected by how many variables we have in total. So if you have more variables, if you have all these thousands and thousands of genes, then you really need to have a very small number of relevant variables. If you have less of them, then you can be a bit more relaxed about it. And this, of course, is again an issue in economics, where so in genetics it might seem logical that you have many genes, but there are only maybe one or a few of them actually which are responsible for causing a certain disease. But in economics, this is pretty hard to argue that of all your variables, only a few actually matter. It's much more likely that quite a bit of them matter. So we have to think about how we can translate this to an economic setting, which I will come back to in the next lectures. All right, a bit about the lambda, the tuning parameter, because we've looked at how to select it in practice. We now also have some theoretical guidelines. In particular, it should grow at the rate of log p over n. Now let's first see what that implies. Well, first, lambda should go to 0, because we know that log p may never grow as fast as n. So we should penalize, but we should not penalize too heavily, which is what I already discussed. If you have too heavy penalties, you put too much to 0 and your bias will not disappear. The larger our p is, the more we should penalize, right? If p is larger, then the numerator will become larger here. And that also makes, of course, perfect sense. If we have to sift through thousands of genes, we have to make sure that we have a higher penalty than if we have just 10 variables actually to choose from. right? You would probably not even want to use the lasso unless you only have very few observations. If p is therefore small, well, we hardly need a penalty, and we really go in the direction of least squares. Now you might be tempted then to say, if I have this rate square root of log p over n, well, I know p and I know n, so I can just calculate that, right? I can just calculate that quantity. Now, that would not be a very smart thing to do, because if I multiply that number by 1 million, it still grows at the same rate, right? As long as I put in ln p over n. But 1 million times ln p over n is the same rate. Also, dividing by 1 million still gives you the same rate. So this rate does not tell you anything about how to choose it in practice. Because in practice we only have one p, we only have one n, and we can multiply and add stuff and so on, and without changing the rate, but of course changing the value. So you really do need an appropriate choice of lambda, not based on this rule, but instead based on, for instance, one of the methods that were discussed in the earlier lecture. So next lecture we'll wrap up the theory. So we'll look at the second part of the theory where we focus not on consistency but on variable selection. So how well is the lasso able to select the right variables? Can we give some guarantees about variable selection? And then as a next step we will look at applying the lasso to economic applications.